Hi, my name is Keenan Hardert. I'm a biology professor at Minnesota State University. I study cancer research and education research, as you can see right here. So today we have principal components analysis and actually principal component regression, but mostly we'll start with PCA, divert into PCR and not the wet lab kind. And we're going to see how we can interpret mass data. So look at what you're looking at here. The main thing that we're going to have to see is like, hey, when you have a ton of data that are all in different scales, for example, it's going to get tough because you're going to need to address multicollinearity, interpret results, know how to work loadings, eigenvalues, all the PCs and stuff. I can't do a full like what is a PCA type of video, but I can definitely show you in Prism what you're looking for, how to utilize it, and how to stay safe while doing so. So you're also going to be able to see the binary outcomes that we want to see on here as well and see how they relate to things. It'll be really good in terms of like some of these big hypothesis generating results. So I've loaded in my class data, random IDs, the hours they work, how many reviews, their GPA. Notice right here, for example, how a GPA only goes up to 4, right? These review numbers are pretty sporadic. Total attendance rates are a lot higher. What's going to happen is a PCA is going to actually make every column of data its own little relative universe. Not quite like a Z-score, but it's going to be able to collect those relative pieces and say, based on your relative strength, you're influencing the total data this much. So as we get into things, we've got a lot of stuff rolling on here, plenty of categorical variables. And in the case of anytime you have, so we have exercise days, for example, and sleep hours, I had to make sure that it said, hey, you have to do continuous because there must have been one in here that said like, I don't know, or something in text. It will likely kick those out. So see how in exam 3, this person had a W. That's not a number. They will likely be kicked out of the analysis, unfortunately. So make sure that if you can help it, have complete data sets. Otherwise, it will take away from you. So let's go ahead and get started. I want to perform, let's do analyze right here. You can also do a correlation matrix, but it's going to make one for us anyway if we do PCA right here. All right, I want to include everybody. Let's go from here. Let's go ahead and do all this. It's only going to take the numerical data anyway. We're going to come back here in a sec. But for options, standardized, fine. Yeah, so basically the mean will become a 0 and standard dev is a 1. So that's kind of like your classic kind of Z-score type of thing. And it's going to just make everybody on the same scale. So now the mean value is what we now call 0 for each one of these. So if the mean value for attendance was like an 88, that is now a 0, for example. So method for selecting PCs. This is probably left to be the default. What you're going to want to say is that you want to be able to explain of all the variance in the data, of the 100%, in most cases, you want to explain at least 70% of that as best as possible. So we're going to see if we can do that here. Like I said, I'm running this data pretty raw, so we'll see. All right, so in here, this is going to make me a PC score table of every row, which is kind of cool. I kind of want to see a category. I want to see if they attended class or not. Let's see how that goes. For the graphs, I would get everything because we will be able to use all of these differently. And you can say, yep, make this for future analyses. Perfect. All right, here we go. So off the bat, here are our results. There's PC1, which is essentially, again, a principal component that is saying, I gobbled up and made the most, I summarized the most possible amounts of the data, essentially. In this case, our first PC did summarize about, or collect about 36% of that. PC2, the next one, which is technically going to be the opposite axis to gobble up the rest of that variance, only did 10. So sadly, for interpretation's sake, I did not reach 70 on this up way until PC5. Ideally, your data should reach 70 within 2, maybe within 3. So that's a consequence sometimes of using data like this, and that's okay. If you didn't notice, I did have a lot of data that had like zeros or like a bunch of things were 100, like attendance or things like that. So kind of always watch out for that. That said, we can still kind of run through here and we can say, hey, here's my standardized normalized data. Remember I promised you that GPAs were gonna go up and down and like a 0 would be the average? There it is. Something called an eigenvalue is also going to be pretty helpful here. The good news on our eigenvalues actually right here is that a value of 1.0 is kind of going to say this vector, as we call it, which we're about to see how vectors go in space and length. These are all powerful enough vectors at 1.0 that we can kind of trust them in this case. So given that, the data wouldn't be too bad to be fair. What we're going to look at here right now, and like it saw, those eigenvalues for these five were there. Here are the contributions of each variable and the direction of each PC as it summarizes it. So as you can tell, most things are going positively towards that PC1, except one thing, the hours working. How heavy are they employed, for example? You can see eigenvalue contributions here, but this is one of my favorite tables right here. For PC1, who was the biggest contributor, for example? Who's the biggest pusher? And this makes a lot of sense right here. Guess who the biggest wholesale push and influence on everybody is? It's the total class percent, right? It's the end game value. That actually makes a lot of sense. And notice how PC2 is the opposite axis and direction of PC1. Hence, you're going to get the opposite for the big values here. So variance versus PC correlation, things like that. PC scores themselves, contributions to each one. And then the last one of my favorites, a friendly correlation matrix, just in case you want to see it. I love looking at, for example, like here's class right here. It is a negative correlation between the hours you're working and class percent. That's not good. There is a higher correlation between how well you do in class and the number of reviews you go. There is a substantial correlation between your existing GPA and how well you did in class. So we want to get into some more advanced stuff than the correlations, though. So let's keep moving on. All right, loadings, let's go. This loading setup is saying for each of your factors, which way did they push? And what the core thing that you're looking for here is who like kind of goes the opposite direction as the others, right? Look at commute and hours working. They are against exercise and sleep and review hours. All the supplement hours, not good, right? And then look at all these factors in here. If I can zoom in, GPA, attendance, class, the exams, all of them, they all varied in the same direction. It means that this pod right here is kind of its own thing. These two are their own pod, and these three are kind of their own pod. And you can sort of see the directions and the clusters, quote unquote, forming here. I don't know if I can actually add onto this one. If I can do, oh, I can totally do this. I can totally do this. Oh, dang it. Oh, it's not gonna do a confidence ellipse because there's just one group in this case. Um, but doing a confidence ellipse around those, probably in another analysis would be fun. Next, I love looking at this, right? These are everybody's value, and it's still put on that PCA scale right here. So if I go here and I'm like, hey, get rid of these labels for me. I don't want to get too busy. Dang, I can change whatever color we're looking at here, but right now I had it as the subcategory for were you a high attender? You came to 90% of classes. Oof, look at that blue. And look at the values of where that blue looks. Here, I'm going to try and show you. Remember where that blue was, right? Let's get rid of these labels one more time. Remember where all those blues were right there? Look where all those positive guys were, right? Check this out. There's the quizzes, the exams, and the attendance. So when those numbers are high, yep, look who's contributing to those good numbers, quote unquote, those high attending students, right? And that's what we're kind of seeing here. So we also already saw the eigenvalues in just straight up text, but this is also not a bad way to visualize like, hey, up to PC4 has pretty good eigenvalues, so we can probably trust those four PCs. Here is my scree plot where we wanted 70% variance explained. We did not actually reach that even with four. So these results sadly would be a little more suspect. Not impossible. Like I've seen PCAs with like 45% explained variance before, but ideally you want 70. That said, what we've got here is an excellent look, an excellent data saying like, wow, these factors amongst all the data that we started with sort of collinearize together when everything's summed up, right? I mean, this is really cool data, honestly, just for me in my work. So let's see what else we can expand on. So I'm going to try something new this time. I want to do another PCA, right? Oh, where's my PCA? Come back here. Multiple variables, PCA. I'm going to include everybody again, right? But this time, what you're going to want to do if you want to do a PCR and do a regression on one of these variables, I'm going to unclick class. That is my king dependent variable, right? That is the king of dependent variables. How'd you do in class? I'm going to go right down here. Once I click that, class is my option, final class percent. All right, I'm going to keep everything the same. going to do symbol color again. I want to do, I want to see, oh, these are symbol fill color. Yeah, I'll do hours working because these are still linear. These are quantitative data right here, not categories. All right, graphs again. Let's do this. But this time it's PCR. I'm after one thing, kind of like our multi-regression. Again, that's what's going to happen. So we're going to still have the same PCA somewhat that we had. This now that I actually removed class as a variable, check this out. I actually do explain enough of the variance with the other stuff. It kind of makes sense that since like class was like the king amount, that's what would happen. But let's look at PCR. Now, just like when we did multiple linear regressions, check out what's happening. Class percent, we've got beta values for all of these guys now, and they're all set up for significance. They're set up for 95% confidence intervals. What influence per point of X to Y are we estimating that hours working have, attendance has on your class percent? So, I mean, looking at this, look at that. Hours working is a negative direction, a negative influence. The more hours you work, the worse you're doing in class. The higher your attendance percent, the better you're doing. Look at all these guys. The better you did on any of these values right here, you did better in class. And remember that in the position from the biplot, right? And then if you had, if these values got higher, you actually did worse. Oh no, that means that sleep and exercise were negative correlates with class. Oh no, or not correlates, kind of influences. Commute being higher also makes sense as a bad thing for class, right? It would lower that. So we can look at our new plots. Again, we see the same setup here now without the class total influence dragging everybody over here. I see now clusters really forming here, really informative for me that, and again, if we, oh, these are our like full piece PCAs right here, biplots. Yep, there they are. Nice. So seeing everybody in here, seeing proportionate variance. Yep. Sorry, I'm bouncing around too much. But what this is going to show you more than anything is that when class, for example, is still considered as the main thing, you still have these excellent clusters over here, collinearizing. You still have the same bad ones. You still have the same kind of questionable ones right there. And again, you are going to have your own values now sort of set up in this massive multiple linear regression that is just going to be excellent, right? So that's our main setup for today. Hopefully that was not too bad. Thanks for joining.